Hello, my geeslings. This is Robinson Earhart, the Mother Goose, again introducing another episode with Haim Gaifman. This should be the third episode. I am recording this introduction with the intention that it will be episode 21, but it might end up being episode 22, or who knows what episode it'll end up being, because Haim likes to look at these before I put them up to make sure that I haven't caught him making a mistake or saying something wrong. And in case that is the case, right now on the video at least, I will be typing some sort of subscript clarifying whatever error was made, and he'll probably ask me to point out that I gave him no time to prepare. Anyway, Haim is super important to me, as you know, if you have listened to any other episodes. He's a computer scientist, a mathematician, a probability theorist, a philosopher at Columbia University. He's also taught at the Hebrew University of Jerusalem and got his PhD at Berkeley from Alfred Tarski. And in this episode, it's more of a, well, it's a meta episode, but not meta in terms of the podcast. It's not about the podcast, but it's meta philosophical in that we start off by talking about what philosophy is. And having talked about this plenty with Haim, he's really changed my ideas of what philosophy is. And then for the most part of the podcast, we talk about what is mathematics. And he has a very idiosyncratic way of answering this question, and one that has taken me a lot of time to understand. But just listening to this podcast episode again yesterday in preparation for releasing it and recording this introduction, it makes more sense to me now that I've heard it a bunch of times. And he's actually teaching a course with Justin Clark Doane on what is mathematics in the philosophy department at Columbia right now that I'm sitting in on. And his thesis basically is that to answer the question, what is mathematics, you shouldn't be seeking to answer questions like what are mathematical objects or how do we know about them, but the answer to the question is really concerns mathematics historically speaking, and how it was developed, how it was used, who used it, the technical developments over the thousands of years since the Greeks, those sorts of things. And as you listen to the episode, you'll get a better understanding of how he views this whole issue. Anyway, this was a wonderful conversation. I have one more that we recorded back in May. This one was recorded in May, even though it should be released sometime in October. And then hopefully, even though I'm across the world in Stanford and he's in New York, we will continue to record some virtually. All right. I hope you enjoy this episode. I really did. I learned a lot from recording it with Haim. And let me know what you think. Now we're going to begin.
Okay.
I see already that you've got some books out here.
This is the most difficult subject of all the subjects you asked me before.
Well, we'll get to that subject later. I see you have Euclid's Elements, but the first thing that I wanted to talk about today is when I came to Columbia to study philosophy, I had an idea of what philosophy was, and it wasn't fully formed, but I thought it was a way of answering questions.
Yes.
And you told me when I asked you what philosophy was that it was not at all about answering questions, and I found that very surprising. You told me instead that philosophy is about gaining insight. And I'm wondering if we can talk a little bit about that right now. So why do you see philosophy that way?
Because the question presupposes already, by posing a question, you have a lot of presuppositions there. And by answering the questions, it is somewhat a legalistic point that if you answer a certain question a certain way, you are already committing yourself to something. For instance, when did you stop smoking? You cannot answer this question without agreeing that you smoked. Okay, so there are presuppositions to every question. And sometimes the very posing of the questions uses a terminology which commits you to something.
So philosophy then can't just be about answering questions, because it also has to be about phrasing them properly.
That is correct. But here we are already presupposing that you do a brand of analytic philosophy.
Okay.
Now there is a...
So there are other, I mean, I know the answer to this, but there are other types of philosophy than analytic?
Yes, there are philosophies that come and tell you what the world is. And they
like a religious philosophy, maybe?
Yes, or mostly... if you look at philosophies, you have Greek philosophy, which is our guideline, but there are also Hindu philosophy, and it is simply a general reflection which expresses attitudes towards the world. And the philosophy is a kind of an inquiry which is supposed to give you a taste of what the world is.
That's what the Greek and Hindu philosophies are like?
In a sense, it's any philosophy.
Okay.
And you can start simply by declaring boldly that this is what you will do, and you start speaking your language. Now, it might be, if it's interesting enough, it may be worthwhile for the listener to learn your language, because if the listener learns your language, the listener might gain certain important insights into life, into reality, into what's called the big words. Okay? Other kind of philosophy starts from, so to speak, a minimalist basis. It doesn't legislate, it doesn't give you a terminology that compels you to follow the intuitions or to understand what somebody is saying.
One philosophy that comes to mind that might be of this sort is phenomenology.
Yes. So but phenomenology already is within a tradition of culture. Philosophy is a certain basic attitude to what has been produced by the human race in the area of thinking. That's all I can say, or the area of thinking, of presenting something. It sums up the intellectual history of the human race, of part of a human race. That is philosophy. I mean, philosophy, the raw materials for philosophy is the history of the human thinking, of the human race, of how we talk, how we think. This is a basic inquiry. And not everything can be a subject of philosophy, although there have been attempts to do a philosophy of anything. Some areas are more naturally given to philosophical analysis than other areas.
Something that Varzi, yes. Achille Varzi, a philosopher at Columbia, was telling me today. Mm-hmm. We had lunch. He told me that he just gave a talk on the philosophy of finance, in mm-hmm. which he was talking about the sorts of objects mm-hmm. that derivatives are. Mm-hmm. And derivatives being options, futures, these yes. sorts of financial instruments. And he told me this sort of stems from maybe concerns about what a $20 bill is. Because on the one hand, a $20 bill is just a piece of matter, mm-hmm. like a star or mm-hmm. a rock or something. Mm-hmm. But in specific contexts, it means something very particular, and in other contexts it doesn't. And so I just found it fascinating that there's a philosophy of finance, which had never occurred to me.
I don't know. To tell you the truth, I don't know exactly what he meant. I mean, philosophy of finance would be part of economics. And economics itself struggles to become its own subject, so to speak, out of the financial history or the way human exchange certain items with other items, giving them a value. So the raw material of economics, of economic theory, would be the practices of the human race when it comes to exchange of goods, to exchange of certain objects, to exchange of certain legal commitments, like signing an IOU and all kinds of legal documents which commits you to produce or to compensate or to pay or to get paid and so on. So this is, again, this is a summing up the brute facts which underlie commerce, which are facts which go very back to very ancient civilization. I suppose when it comes to gather hunters or previous, there would be no economics.
Right. When you say that philosophy has as its raw materials the history of human thinking, what that brings to mind for me is how I tend to answer questions from my friends or family about what philosophy is and what I'm doing in particular with regard to philosophy of math, which what we'll get to in a bit. But I think of philosophy as I'm interested in it is looking at sort of the assumptions and the principles and the larger questions around pre-existing bodies of human knowledge. So mathematicians go about their work tending not to think during their work week about what the number 2 is or what a function is or how we know about these purported objects. And it's one task of philosophy to go into subjects like mathematics and then look at what really is going on, the epistemological questions, the metaphysical questions, if there are any, to look at mathematical practice. And it's in this sense that I've come to understand what you meant by philosophy being a way of giving us insight, as opposed to trying to answer questions.
I don't think that every subject is equally can be a subject of philosophy. I doubt that you can speak about philosophy of baseball, for instance. You can describe the game and so on, but the philosophy would be very thin or artificial.
Right, but there's certainly philosophy of games in general.
Well, it depends. Again, there is a theory of games. You can speak about games in the sense of that Wittgenstein has spoken about language games and things like that. Mm-hmm. But games, just in general, I don't know.
But something else that you told me to substantiate your point that philosophy is not about answering questions is that all philosophical programs have failed. So whereas
it's a very wide declaration. Some of them had partial results. I don't know in what sense you can say that phenomenalism failed. Okay. The positive philosophy, they themselves came to acknowledge that there are certain questions in which they couldn't carry out the program. And So it has become a fact that certain attempts were recognized as not leading to anything, but this was a very valuable lesson. And in a sense, the fact that a school can say, well, this presupposition and so on, we couldn't make it, gives you a ground to treat that school more seriously, or give it bigger honors, if you can, in quotes, than other philosophy who always argue that they were successful because, and then they bring all kinds of arguments why this and this. So an attempt which ends by an agreed failure is an important enterprise which reveals something. That means in philosophy, the goal is not to succeed, but to gain insight. And some philosophies that want to show you that no matter what, they succeeded and so on, end up by giving twisted arguments in which to legalize their status.
So,
one addition, I would say philosophy of any subject should be related to subjects which have a definitive cognitive dimension.
what do you mean by that?
For instance, if you take a football, it's a game. You have to have good mass, you have to have good instincts and so on. But as against philosophy of science, science by definition is a matter of cognition, of thinking, of something perhaps which is truth, of certain claims in which success means success in having new scientific results, new true results, and so on. I wouldn't say that a physical game, which is extremely enjoyable and important and so on, is by itself a subject which has a strong cognitive element, because it is a subject in which you have a lot of training to do, a lot of bodily feeling, and so on. So you cannot speak of a philosophy of the body or something like that, unless you use philosophy in a very wide sense, in which you say, my philosophy of life is,
Right.
That kind of thing.
Right. So that brings us then to a topic very dear to your heart, and which is mathematics. And one of the questions that I've found burning in my mind for some time is, what is mathematics? And that's a big question.
Yes.
A huge question.
Yes.
And it encompasses many sub-questions, such as what are the objects of mathematics, if there are objects? What unifies mathematical practice? How do we how do we acquire mathematical knowledge? But when you hear the question, what is mathematics, where do you start?
I start by mathematics as a discipline which had an historical place, which started at a certain year, and which we developed and changed during these years. The whole big body of mathematics as it developed during the years, as part of the history of the human race.
Okay, so you first and foremost, when confronted with the question, what is math, look at its development over time.
Yes,
and see how it was used.
Look where you encounter math.
That seems like a very commonsensical answer.
Yes, I mean, you must give you what is math. I don't want to give you an a priori answer, or to give you some clever trick or some formulation what it is. Or if it is a formulation, it should be rooted in pointing to, okay, you look at what Euclid did, you look at what this did, then you can see here is math. Now, in some areas, we would say the math is faulty or has to be corrected and things like that. But definitely, I think Euclid is a good point to start
Okay.
because these were mathematicians who were aware of the need to give an account or some explanation what they are doing.
Hmm. When I think of the history of mathematics, the first thing I think of isn't even humans, but pre-humans, or even today they do experiments on dogs or crows or
Yes.
monkeys, and that seems to be a good place to think about where.
Well, I would say I don't know if you will have a philosophy of it, but you will have a certain abilities which you will connect to mathematical abilities. I don't think there is a philosophy of math as it is conceived by chimpanzees.
Right,
Although
I'm not suggesting that there should be a philosophy of chimpanzee mathematics,
uh,
but their
there are,
numerical abilities
yes.
suggest how ours originated,
Well,
or why ours
no,
originated.
no. It's a useful point to ask what are the mathematical patterns of recognitions, because knowing certain math or being able practically to distinguish 9 pieces of cake from 12 pieces of cake,
Very important for me.
yes, is important for the animal that likes cakes
Hmm.
in that sense, or
Right.
can make choices.
And I mean, it's probably important originally to keep track of your children, or the eggs in your nest, or any number of other things.
Yeah, well, children, you would say, if you don't know how many children you have, you either must be a very king or leader who doesn't know already how many wives he has, because he has thousands or hundreds or something like that.
Yes.
But simply, if you give two hips, one hips of which contains more pieces of food or more grains and so on, and the animal is given the choice going to this one or that one, you can see what are the mathematical abilities of animals,
Hmm.
which are not necessarily the more advanced. I mean, you can do it. Well, I don't know about birds whether they are or not advanced. Now there are all kinds of claims being about the intelligence of birds, but in any case, you can actually conduct experiments in which you see what the counting comparison by way of uh, counting a collection of discrete units, which are each one of them is more or less valued in the same way.
Hmm. But so then, going on to humans, presumably, and obviously this is conjecture because I'm not an archaeologist or
Yeah.
a psychologist, but I imagine that numerical literacy or numeracy arose one for commerce and trade. Uh,
Yeah,
that's how it was initially used, and then
actually, I think it was, yeah, this for sure, but it was used in engineering, in construction, and in the need to count how many stones are needed for this and this, how much raw material, and also about value when you have to change one for the other, and so on and so forth, endlessly. And these are all practices in which you have some sort of scale of quantity with respect to a certain kind of certain kind
unit
of
maybe.
yeah, no, but a certain kind of uh, material objects like tiles, like number of stones and things like that.
And then presumably, I mean, mathematics became an abstract practice after that.
No, the abstraction might have come even without people noticing it. There's an ancient mathematics which deals with natural numbers, which consists of producing abaci, an abacus,
Mm-hmm.
simply to enable a shopkeeper to make very fast calculations, to know whether he lost, how much he gained, and things like that. And people with abaci, and with knowledge how to manipulate an abaci, are now rare because you don't need it. But in the past, there were people who could do it just like, almost like in computational speed, you might say.
And why do you consider that abstraction? Just because?
Because the abaci, by themselves, they don't represent, uh, they themselves have no value. Their value is that you are enabled to calculate how much you will gain or lose if you agree to a certain trade.
And it's independent of the objects that the little
Yes,
stones
right,
represent.
right. Whether suppose you sell for this and you get for this, and every one of these costs 3 coins, and every one of these you have to produce cost you like that, and so on. So you are a small shopkeeper, and you have to, at the end of the day, to make a very fast calculation how much what were you expended and how much you got. And how much you got, you have for the records of this was sold by me at that and that price, this I bought at that and that price, bookkeeping.
So it seems like, at least initially, based on the sort of story you're telling or way of presenting how mathematics was first used, that it's at least on a very primitive level a way of organizing things, a way of performing calculations, a way of bookkeeping, to use your word, a way of taking measurements.
Yeah.
Okay. So
Counting how many packages of sand will be needed in order to construct this structure in which sand is a component. Or you have earth and sand or whatever they use to produce the pyramid. I mean, this was a huge engineering job. So all kinds of ancient engineerings involved math.
okay. So this is the initial story before mathematics, I think, really became a discipline. But what's the next step in this sort of history that we're constructing?
Look, if we go from if we in Greek established not only math, it established philosophy. I mean, at least in the Western tradition. Philosophy as a general subject begins there, and it might be natural that they regarded their mathematical activity as part of a general view of the world. So it was very natural for them to give a certain view of the world which is very much related to mathematical activity.
I'm not sure I totally understand what you mean here.
Okay, you know that there has been Pythagorean, and there's been
Pythagoras.
Yes, but there was a school of Pythagoreanism,
Yes.
and they developed the technique of making a lot of calculations and estimates and what we would call now arithmetic, or for instance summation of an arithmetic series, or summations of cubic series, 1 to the cube plus 2 to the cube plus 4 to the cube plus 3 to the cube, and so on. And they did it using geometrical models
Okay.
and using geometrical argument how to do that. And multiplication is very easy to do because a multiplication is a product, and which gives you essentially not the area but the number of squares in a rectangle, in a discrete rectangle. And then it is obvious if you just rotate the rectangle that a times b is equals to b times a, because it's simply the same thing, but just rotate it like that. So you had it from geometry. And so they had the commutative law for addition and multiplication, and the distributive law for multiplication over addition right there from geometry.
But you said something about them viewing mathematics as part of the world. It was part of their philosophy.
It wasn't part of the world. It was, they took mathematics to give the basic form of physical reality, in as much as physical reality can be captured in this way.
Well, isn't that also, I think, how Euclid viewed his geometry? It wasn't necessarily... he viewed it almost more as physics than as
No,
math.
I wouldn't say so.
You wouldn't say that?
No, definitely not.
But I thought that he viewed the geometry that he was developing as his geometry was the geometry of the world.
That is true. The geometry was supposed to reflect, to give the basic properties of physical space.
Right.
Yes. It doesn't mean that physics...
Right.
This would be true of Archimedes, in which kind of realized that you can have the same kind of axiomatic method can be applied also to theoretical physics. And he used and developed a lot of models which were based on physics, and he was a genius engineer at the same time that he was a mathematician.
But anyway, going back to the broader question, what does this tell us then about what mathematics is?
Mathematics for
the Pythagoreans and the Greeks in general, what does talking about this tell us about what mathematics is?
Okay, so for them, mathematics gave the basic properties of physical space, because their mathematics was geometry. And it was a very explicit idealization. That means you get the forms of the physical space by considering a certain idealization.
And is that Euclid or the Pythagoreans as well?
I think we don't have Pythagorean big mathematical tracts like we have Euclid.
Okay.
But they had their tradition, and there are stories about them. But the story of a really huge discipline, geometry, two-dimensional and three-dimensional geometry, is given in the 3 volumes of Euclid's Elements. And if you look at what Euclid does, you can see that they are defining the mathematical entities as a kind of a limit case of an idealization of the actual physical objects. And you can see it from the definitions. So Euclid starts by definitions. There's a whole lot of definition. What is a point? What is a line? And what is a geometric figure, and so on. And you can see that they do it by idealizing the properties of a point and so on. So that's why I brought it. And here it gives a long list of definitions. Okay.
So for those who aren't watching, Haim has taken out a flashlight and is now reading through Euclid's Elements for me.
Okay. So a point is that which has no part.
Right.
Okay.
And that's obviously an idealization because there are no such things.
Yes. So, but they treated them, they didn't get whether there is or there is not. They gave you straight away the idealization.
So you're saying they're not asking philosophical questions yet, asking, what is a point?
Well, I don't know that for them this was not also a philosophical question.
Okay.
But these definitions is not the reason that Euclid is such a big classic book of mathematics. You can teach Euclid without having these definitions. This is not what gives what Euclid is known. Euclid is known by developing a very sophisticated and difficult mathematics, proving theorems and providing constructions using a straight edge and a ruler. This was their standard way of constructing. This was, so to speak, the rules of the game, that for them a construction meant that you can draw a circle with a given center and a given radius. Okay? So you have this, and then you have a straight edge. Am I clear?
Yes. We do that in high school in the United States.
Yes. You take this,
A protractor.
a protractor, or,
Yeah. That's what it's called.
This is the English term. I know the Hebrew one. The Israeli
What is it in Hebrew?
mechoga, something which makes circles.
Oh, that's a nice word.
But you have two legs, and you put one leg here, and then
you spin it around.
and so you can construct a circle, and you have a straight edge. So this is the way they did it, and in Euclid, the propositions, what is called propositions, consists of claims, which is theorems, but there are propositions that this and this can be done, which shows you how to make a certain construction. These are also propositions. So Euclid, the body of Euclid, the way why it is so impressive, is the list of propositions and the way it derives it from the axioms.
So two things now have come up for me that we've mentioned, or two things that I've gotten out of what we've discussed so far, is that mathematics originated as a way, very roughly, of organizing information, and then
organizing the world. Yes.
Okay. By organizing the world,
certain aspects of the world.
The tiles or money exchanges like
money,
that. I'm just
or
using
packages or
information very loosely.
Okay.
And then the second thing that comes to mind is now with Euclid, this is becoming more formal and also more abstract.
Yeah, that's true. But the actual engineering consists pails of water, how many pails of sand, and so on. How many cubic measures of this material or this material. They were engineers.
Mm-hmm.
Those who constructed the pyramids.
So do you want to, is there more to say about Euclid now?
Oh, yeah.
Well, I know that there's plenty more to say about Euclid in general, but in the context of this question, what is mathematics, is there more to talk about Euclid right now, or should we move on?
Euclid is the great example. I think what I'm claiming now is an actual fact. I verified it once. I don't know that I have the source there, but in Britain, at the beginning of the 20th century, Euclid was used as a textbook for geometry. And I think I gave you this example. You cannot imagine that any physical science, any natural science, could have used at the beginning of the 20th century a textbook that was written at the time of Aristotle.
Right. Well, that brings into light another peculiar quality of mathematics.
Yes.
Which you've to quote you.
Yes.
There is no phlogiston or phlogiston in mathematics. So the natural sciences go through revolutions in which whole swaths of information or theories are abandoned, whereas mathematics does go through sort of fads and trends, and areas of inquiry are sort of abandoned. But once something is proven, it's proven.
Well, that's not completely precise.
Well, yeah, I'm not going for complete precision.
No,
here.
I want to make it precise.
Okay.
Because from our point of view, and I think we are justified, the proofs in Euclid, some of them are defective That means they use various reasonings which is not given in the axioms. And they assume that you can, for instance, move a triangle until it comes to a certain place. They give all kinds of arguments which are not guaranteed in the axioms.
Well, I'm not saying that people can't have made mistakes that will be corrected,
Yeah,
but once something is proven in mathematics,
yes,
then it can't be unproven, so to speak.
that is correct.
And
That
in that
means
sense, there's no phlogiston.
I don't know. Look, this is an empirical claim. There is no published textbook in mathematics which would simply will be thrown and say this is all nonsense.
Right.
Okay, I know there are certain counterexamples, and I wonder if you realize what is a good counterexample to that.
You're asking me if I can come up with a good Cantor example?
The author of a book in geometry which is nowadays completely valueless because all the proofs are incorrect.
Huh.
The name is Hobbes.
Oh, no, I wouldn't have guessed that.
Yes. So Hobbes was a very smart guy, and he was a very... his first name is John, right? John.
Thomas Hobbes.
Oh, Thomas Hobbes.
John Locke.
Okay.
John Locke, Thomas Hobbes.
Okay, Thomas Hobbes. So Thomas Hobbes was a very elegant writer, and he had a...
Leviathan was...
Yeah, yes. And one of the establishers of political philosophy. Okay. What is less known is that he wrote books in geometry. Hobbes came rather late in life. After he studied other things and so on, he happened to come upon Euclid. And then he opened it and he saw the proofs and he says, this is marvelous. This is incredible. He was so, you can do... And then he started working and said, well, I have a theorem which how to trisect an angle, an angle and so on and so forth. There have been the well-known problems of antiquity, the doubling of the cube and the trisection of the angle. And there was another, I forgot the three classical problems of geometry. Trisection of the angle, doubling of the cube. This was...
I can look it up.
Look it up. What was the third one? It is...
Three classical problems.
No. The circle. Producing...
Squaring the circle?
Squaring the circle. Producing a square whose area is the same as the area of a given circle.
Mm-hmm. Doubling the volume of a cube.
Yes, this is all you suppose you have two... two altars you sacrifice.
Two altars.
Yes, two altars. You sacrifice on them. And then you want to build an altar whose volume is double the sum of the volumes of the two altars. This was a kind of the story of that. But it's, yes, the doubling of the cube, that means find the cube whose volume is double of the volume of the cube. Construct, this was supposed to be geometrical constructions. So you give me the length of the side of a cube, and using a straight edge and the protractor, you have to construct another cube whose area is double the area of this cube. Okay. So what you are given a segment, and you have to construct another segment. The segment will be the size of the cube. And The same goes for squaring the circle, and the same going for dividing an angle to 3 equal angles.
And so your point was just that Thomas Hobbes thought he might have solved some of these.
He was sure that he solved
but
one.
But he didn't, so it all had to be gotten rid of.
It's an interesting, because I looked into what he did, and it's very vague. It's not at all clear.
Well, he was dumb.
He wasn't dumb. He was a sharp guy, and he thought that he could do it like that. No, there's an involved construction there, but somehow it is not correct, and it's difficult to see because it is a little bit vague how exactly it works. Eventually, it became kind of a game almost between Thomas Hobbes and another mathematician whose name escapes me, who was a serious mathematician, British mathematician. You say this is nonsense, you didn't do it. And then they asked for the French Academy to judge. It wasn't whether... And after a long debate and so on, they came and judged, and the verdict went against Hobbes. But Hobbes was also a very ambitious person, and his goal was really to become famous. By that time, this story was not very interesting to him, because he published his writings on political philosophy and Leviathan and made himself a worldwide name. Mm-hmm. So he got his own satisfaction from becoming famous and well known from his political writings, and for the nice style. I mean, the style is incredible.
All right, I'm going to have to pull you back to Euclid again.
Okay.
Or maybe, are we moving on from Euclid?
No. So now in Euclid there are defects, but it was recognized that this was the right way to do it, and this final solution came, or the final crowning of this work came in the work of Hilbert from 1891.
When he gave a complete axiomatization of Euclidean
not
geometry.
only of this geometry, but all kinds of other geometries.
Hyperbolic and...
He gave examples that these axioms... He gave counter-examples showing that these axioms do not imply this, and a lot of other meta-claims about the system. But essentially, he gave a way of axiomatization of Euclid, since that there are other axiomatizations of Euclid.
But again, so what this tells me, though, again, is that we're moving from just organizing the world to giving various ways of organizing abstract information.
It's a form of... It is an idealist form, which is completely precise, which admits of no vagueness or not clearness, which goes with empirical science, because it is not an empirical science.
Even though it began...
Look, they thought, the Pythagoreans thought that the world was rational. They discovered the...
When you say that they thought the world was rational, what do you mean?
The world is something that is given... they had a notion of rationality. And according to them, a rational quantity was either a natural numbers, which is a collection of discrete items, if you want it, or fractions.
So when you say that the world is rational, or they believe that the world is rational, they believe that all quantities could be expressed as a ratio of two natural numbers.
That is correct.
Okay.
But then they discovered that the diagonal of
a square was not rational.
Was not rational.
So it could not be expressed as a ratio of two integers.
Yes, and that brought a big crisis, and there are all kinds of legends and stories about it. Most of them probably dubious. That one story goes that they killed the one who first published it, because it shows that there was something wrong with their whole conception of the world. But as a matter of fact, this irrationality, and that is very much well treated in the volumes of Euclid by
And Eudoxus.
Eudoxus.
Yeah.
Eudoxus is the one that does it. So the part of Euclid which is impressive is that it's extremely high sophisticated mathematics and very difficult proof.
Okay.
No question about it. Ingenious, difficult proof. That is what gives it the aura of being the classic work in mathematics.
But what does it tell us about what mathematics is then, in a phrase?
It is it is a system based on a certain idealization, which admits of incontrovertible proofs, secure proofs, which gives you a certain way of organizing the space.
To me, while I'm sympathetic to a lot of that,
Well, they thought the big point came in when they started looking into it and found and asked if there are other ways of organizing the same material, which is not Euclidean geometry, and this brings you to the discovery of non-Euclidean geometry. So the point that Kant made that these are a priori, they are synthetic because they involve a certain geometrical view, they are not purely logical. And I think Kant was right. You need axioms which are not logical axioms. But Kant was wrong in thinking that this was the only way of doing it. So there are other ways of doing it. Mathematics consists of extending this method, which is completely precise, which has no vagueness in it that empirical science has, doesn't depend on experiment, extending it to cover more and more domains and more possibilities. So you have numbers which are commutative, and then you use rings or fields which are not commutative. And then sometimes you go to even very abstract systems. And all of them can be treated as a piece of mathematics. So it is...
so what is it that unifies the fields and the rings and what Euclid did? And
the method of... The point is that they share certain properties. For instance, there is a commutative field, or what used to be called the skew field, which is not commutative. A field is by definition some... well, there is a definition of a field. This is a collection of...
a domain,
a domain
with two operations.
With two operations, plus and multiplication.
Identity elements.
And yes, identity elements for both of them. So like a group, you have this group and this group, and so on. This is a kind of a structure of this form. And there are axioms, and you derive other from these axioms. Using these axioms, you derive other. Now, this can become very abstract, but still the method persists. That means logic itself can be treated in this way as a mathematical system. And in logic, there are different logics, and you might have debates about what logic is, whether it should be intuitionistic or non-intuitionistic or finite, in the Hilbertian sense, only actual infinity, and so on. But when you go and see how the debates go on and what the people are doing, all of them are doing mathematics.
So you say that
I can be a non-intuitionist or somebody who is completely uncommitted as whether one should be or not be an intuitionist.
An intuitionist is what?
Intuitionist is logic in which...
intuitionistic logic is a logic, but intuitionism itself is a foundational philosophy of mathematics.
Well, that you use a logic which is intuitionistic logic in the proof.
Right, but what they think of mathematics as being something that's in the mind, roughly.
It is in the mind no matter what mathematics is.
No, many people think that mathematics. Well, so you're making the assumption that mathematics is a practice, but other people might say that mathematics is what's existing in some other universe, a Platonic realm, and you're dismissing that immediately.
No, I mean, this is just a gross. Look,
Right. That's all.
put it like that. First of all, the Greek didn't consider the possibility that there will be non-Euclidean geometry.
Right.
Okay, so from that point of view, it is, if you want, you can say they consider that there are Platonic. Platonism is a kind of, it goes nicely with this because it is a realm which is obtained by idealization and which gives you, in this idealization, certain properties which you might want to say are the essence of the essence of a line. It is a length which has no breadth and no depth.
Mm-hmm.
Okay, some essential properties or some, and you can, from this you can use Platonic forms as your philosophy of mathematics. And you might want to say that in Euclid the straight lines were part of a Platonic form or Platonic entities. Okay, some entities in which everything is precise and which is what we call Platonistic, Platonic form. But there is no commitment to viewing it in, there should be no commitment to viewing mathematics in this way. And those who think that there is a big problem with mathematical objects simply don't realize that mathematics doesn't, the Platonists' mathematics is not the mathematics of mathematicians today.
So what I'm learning from you right now, or realizing based on what you're telling me, is that when I'm asking the question, what is mathematics, the way that you're answering it is by explaining to me the nature of the practice.
Yes.
Whereas when I was initially asking the question, when I initially asked the question, what is mathematics,
it's what is done by mathematicians.
Right. That's not what I had loaded into the question. What I had loaded into the question is, what are the objects? How do we know about them? And I sort of expected your answer to...
This is a bad question.
Right.
I think it's a bad question. Look, suppose
tell me why it's a bad question to ask what numbers are.
Because the numbers...
Or what sets are.
Okay.
Or what triangles are.
Okay. Imagine an abacus.
Okay.
Okay. On the abacus are various symbols. You know, they are the
stones or beads or whatever they are.
The bead, you use beads, and the beads has various colors and so on. And you might as well say that there are numbers written on the beads and so on.
Sure.
And the whole function of these beads is like having what do you call it? When you in the casino, you get chips.
Yes.
with this, and you ask, what is a chips? And they say, you now start worrying what kind of entity is this? Is a chip?
I think that's a worthwhile question to ask.
No, what is a chip? A chip is a physical item and so on.
But that goes back to what Varzi and I were talking about earlier, in that a chip is not just a physical object. I mean, on some level it is, but in certain contexts, the chip, like a casino, it means something. It has a value. Whereas on Mars, if we discovered a chip there, I mean, it wouldn't have that same meaning.
That is correct. That is certainly correct. So are natural numbers. Natural numbers are the same, get their meaning in the way they are being used. This is what gives them their meaning. It's not that some sort of entities like a piece of stone that on Mars it is not what it is on Earth.
Right. Well, that is what some people think, is that
Yeah.
there are objects that are numbers. But
Yes, but the whole question is ridiculous, because numbers, if by objects they mean some physical object, their ontology is a completely different ontology from the ontology of mathematics, in which the numbers themselves gets their whole meaning and their whole status in the way that they figure out and they are used in the system. It is like in a casino that the chip is much more than the physical object, because the chip has a value and you can move the chip from here to here and push it there and bet on it and so on.
when you phrase it that way, though, you strike me as a structuralist about mathematics, in which mathematical objects are sort of the idealizations of their properties. So the number 2 isn't an object,
But
it's just whatever is second in a progression.
But I don't, that might be also, but this is not the only way in which you can do it. You can do it in many ways. The natural numbers come out, yes, if you want to speak it in the context of a progression, yes. In the context of a commutative group or an ordered group, in a commutative group or an ordered group, you have another. So these same numbers appear in commutative fields, non-commutative fields, and so on. So the structure itself should be addressed from this wide point of view. The trouble with philosophers, particular philosophers of mathematics, said, oh no, the whole thing is just structure. Now let us give what is a structure. And they start getting into the same old difficulty as before.
Right.
So they want to give some sort of, they can handle it.
Right.
This is Stone Age ontology, you know.
So
you know what the Johnson said. I told you the story.
Something about kicking a rock.
Yes, I mean, Sam Johnson, the one who wrote the English dictionary, the great guy, 18th century, 17th, 18th century. And he had about Bishop Berkeley. And he said, Bishop Berkeley, an idealist, thinks there's no physical reality. It's all ideas in the brains of people or in the minds of people. And since we must have something which is there, even if people are not, they are all ideas in the brain of God, Mm-hmm. So Berkeley and philosophy, okay? And so Sam Johnson was told about it, and he said, "I refute him thus," and he gave a kick to a stone. So, for an object is something that you can kick around, and initially it is the same intuition. An object is something that you must have causal relation. You must be able to grab it. It must be able to hit another object. How can you know about such things that have no causal relations?
Right.
There are no causal relations.
Well, that goes to my next question: is how do you answer epistemic challenges about mathematics?
Yes, because we know
that if we take this book and we take that book, they make two books from experience. But then, how are we able to prove or say that we know that such claims hold generally? And then how are we able to make such claims as the continuum is larger than the size of
that is a different step
of the natural numbers?
That is a different step. My dear, this is a different step.
Well, the idea is that these can be verified empirically, in theory at least.
No, they
questions
cannot be,
about the books, that 1 + 1 = 2, or we have two objects if we hit. But we can't do the same thing when we're talking about infinite collections.
But that is not what 1 + 1 really means.
So what does it really mean then, and how do we know that? How do we really know that 1 + 1 = 2, if it's not insight into some abstract realm? And obviously I'm playing devil's advocate here.
Yes, obviously. And I have to answer you. And that is that I'll give the Frege answer, although I don't agree with it, because in principle that there might be an arithmetic which is completely different had the empirical world be radically different. Okay?
Mm-hmm.
But when you teach children mathematics, you teach them using physical models. Okay? You give them the practice of counting. Okay? But the meaning of 3 plus 5 equals 8 it doesn't mean that if you have 3 marbles here and 5 marbles here, and you take both of them and put them into a box, and then you open the box, there will be 8 marbles. This is not the meaning of that. The meaning is an abstract meaning. The meaning is that if these numbers are objects, that is true that they are abstract objects, but they are abstract objects that are used in the organization of the world. So their meaning comes from the meaning of the way they function in the system, like the meaning of a chip in a casino comes from the way it functions in a casino. It's not just the physical symbols which is used.
So then how do we learn about these abstract objects?
We learn because these are the rules of our language. These are the rules of our thinking. You learn it the way you learn a native language. That's where you know it. And
so in that sense,
you don't need to have a causal relation. The relation is much deeper than that. This is the way we think.
So it's closer, in a sense, to learning how we ride a bike than it is learning that it's raining. I mean, we learn about numbers sort of by doing mathematics and by thinking in a certain way. We don't learn about mathematics by peering into an abstract realm.
The analogy there is not riding a bicycle, but speaking a native language. How do you learn this? How do you know that Tom is good and ugly is equivalent to Tom is good and Tom is ugly?
But from experience and perhaps from some wiring in the brain.
No, by being embedded in a...
Right, well, that's what experience meant.
Well, this is not experience with the world. This is an experience by interacting with other human beings.
Well, the world, that's part of the world.
Okay, fine. If you want to have that, that's
I do
fine.
want to have that.
No, because it's a human institution.
But there's a disanalogy between these two cases that's very important, which is there isn't something objective in a sense about the human language. It's still something that is arbitrary and up to evolutionary accident. But 2 plus 2 equals 4 is not like that. There's something objective about it.
That is true.
So how do you address this disanalogy?
Okay. Since you know, you recognize the idealization that involves in using natural numbers, okay, you can see that this is, you recognize the validity of such statements just by thinking of them or by deriving them from other statements whose validity has been established before. Eventually you will need a proof. So either they are self-evident, almost an axiom, or you need a proof. That's all.
Okay. That I can accept. And so we've gotten a couple of things out of this conversation so far. One, we've described the practice of mathematics using history a bit as something that relies on proofs, comes from or builds theorems based on initial assumptions. It's a way of organizing material in the world.
This is axiomatic method.
Right. And we've also then talked a bit about what mathematics isn't, what its objects aren't,
Yes.
and how we know about it, which were
Right.
some of my other questions.
Right.
The last thing that I'd like to ask about today is, in discussing this question in the past, you've liked to use the example of tiling problems to explain what mathematics is. And
I had to explain the beauty of mathematics.
okay, so you don't view them as a good example for describing what mathematics is.
Mathematics can be beautiful or not beautiful.
Okay, well let's I guess the last few minutes then talk about a tiling problem and how it shows what mathematical beauty is.
Okay, so look,
So what's a tiling
mathematicians.
problem?
Okay, shall I can. Well, okay.
You can describe it because I
Okay,
could
you have.
understand it.
Okay, so this would be come to the presentation at Cornell.
Yeah.
Okay, so imagine a board of 10 times 10.
So
A square board divided into 100 little squares.
yes.
The sizes of the board are squares, are segments of length. Each segment is divided into 10 equal
Right. Well,
segments.
we can just imagine a chessboard sort of construction.
No, I want 10 times 10.
Okay, but 10 times 10.
10 times, like a chessboard by 10 times 10. A
And-
board of 10 by 10.
And no coloring or coloring?
No, nothing.
Nothing at this point.
Okay,
Just 100 squares.
You give away the whole thing.
Yeah, nobody has any idea.
You are a spoiler.
Nobody has any idea.
No,
Well,
no.
Keep going.
Okay. Now the point is, now you have dominoes. Every domino consists of 2 squares arranged in a rectangle, but the length is twice as much as the breadth, right? So it's divided. And the tiling is a covering of the board in which every tile covers 2 squares of the board. There's no overlap between tiles, and tiles don't go beyond the boundaries of the board. Okay?
Sure.
Now it's very easy to tile a board of 10 by 10 by tiling, first of all, say the first row 5 tiles, 5 tiles, 5 tiles, 5 tiles, and so on, and you get the tiling of the board, right?
Yes.
Or you get another one, the columns, 5 tiles, the columns, and you
Yes.
get the tiling of the board.
Because five tiles times 2 equals 10 spaces.
Yeah, 10,
so you
10
just need
squares
50
and
tiles
so
and
right.
you
That's all. Now suppose I mutilate the board by cutting out one of the squares. The square that is being cut can be in any place of the board. So in the picture it will appear like white space.
So there are 99 squares now.
So obviously they cannot be tiled because
Right.
every tile covers 2 squares, and therefore there must be an even number of squares, and here there's odd number of squares. This cannot be tiled. This is trivial.
Yes.
Now suppose I mutilate the board by taking out 2 tiles. Now you have 98. And the question, so the argument from the being that requires an even number of squares doesn't, the previous argument, trivial, doesn't work here because the number of squares is still, the number of them is an even number. The number of the
But
square.
you can't just easily go down anymore
Yes,
or across.
yes,
the way
you can. That is correct. And the question is, can in general this be also?
Can in general what be
This
also?
be tiled? If
If it's an even number, can it in general be tiled?
Right.
That's the question. Provided it's not a complete board.
right.
Okay. And we already know that if it's an odd number of tiles,
Yes.
it can't
okay.
be tiled.
Okay.
An odd number of squares.
Okay. So the standard example which you give is you take one corner of the board out, and then you cut out the diagonal corner at the other end, and can this board be tiled?
Yes.
And it's very difficult question to answer.
To prove in pure mathematics.
Yes, in pure mathematics, you have to prove, or even to find an answer, the right answer, okay, because it's 98. Now there's an ingenious idea. You color the board like a chessboard, but here it is a board of 10 times 10.
Okay.
And you suppose you color it red and black or something
Sure.
like that, because the white will be used for
The blank squares.
for the mutilated square which is
Yeah.
missing. So you have two colors. Now, if you look at the diagonal, you see that you will have the same color in both ends, at both ends, if it's like a chessboard. In a chessboard, it's obvious, but it's true for any board which has an even number, side even
Yes.
number, that it will be the same color. Every tile, on the other hand, must cover adjacent squares,
Right.
which will have different colors.
In this case, then you have 48 red squares and 50 black squares.
Yes, and then you cannot. Therefore, so this is a conclusive argument. Now, this is an ingenious trick, and the ingenuity comes from the fact that, first of all, the original question didn't refer to colors. I added another dimension to the whole setup and induced another factor here, and this factor helps to solve a problem in whose statement this factor did not exist. And this is a very known technique in mathematics. You take a certain mathematical entity, you modify it by adding an additional parameters or and you answer a problem which relates to the original entity without the additional machinery. You impose on it additional machinery and you solve it. And you don't need actually the additional machinery for stating the problem. The problem and the answer make sense without the additional machinery. The additional machinery shows that you cannot do it, that something is not doable. This is the beauty of it. And the beauty comes from a high satisfaction, which is epistemic satisfaction, as if you have here something which is blurred, somewhat blurred, and you don't know what is going there and how it is, and so on and so forth. And all of a sudden, you say, okay, now look, shift a little bit your head, go like this, and you put lights on it, you see the whole thing.
Mm-hmm.
That's beautiful.
So beauty in mathematics with this
Is
story
episteme, is a simplicity, ingenious, epistemic trick which gives you an epistemic satisfaction.
So it's something, it has to do with encountering the unexpected.
Yes.
It has to do with
but it is
simplicity and elegance.
Elegance, but the point is that what the goal is epistemic clarity. So it's all operates in the epistemic clarity domain. And that is why it's beautiful. We are satisfied that it is so satisfying. We are amazing. We see it is amazing, ingenious, and so on. We have a nice feeling about it.
Are there other aspects to mathematical beauty that don't figure into this particular problem?
I don't think so.
Okay, so it all reduces to this epistemic
beauty. Yeah. Now, sometimes the establishment of an additional way of looking, or you establish a very complicated additional organization which can take years in, but then this additional organization helps you to solve scores of problems which were opaque before. So it is a little trick in a game, and you see it in 5 minutes. These 5 minutes can be translated into 5 years, into developing an additional structure which you can be imposed on the additional,
It's okay.
Which you can impose on the original problem, so that you can give an account which solves a whole list of problems which are otherwise difficult. This is what category theory does.
So this actually, I think, brings us back to my first question of the evening. So we talked about what mathematics is as a practice, and we've now done a little bit of philosophy of mathematics,
Okay.
which is, if philosophy is about bringing insights to aspects of human cognitive activity, we've just described
Yes.
what is beautiful about mathematics.
Right.
So that's sort of what one thing that philosophy
Right.
can contribute to mathematics.
Now, not every problem in mathematics can be solved in a beautiful way, even in category theory. And the hardest problem in mathematics are in, let's say, classical mathematics, which is mainly mathematics in which algebra, calculus, geometry, and things like that, not logic, not set theory. Set theory is a different area altogether.
Right.
But traditional mathematics, like the Riemann conjecture, or hard problems in the calculus or differential equations and so on, might require the use of computers to solve the problem, or to some sort of organization in which you rely on other results that you take for granted. Okay, there are all kinds of tricks, probabilistic methods, and things like that. That essentially you obtain as given some brute facts which you don't go into. And these are ugly solutions. But ugly solutions have solved many problems where there's no other solutions.
Like Apéry's proof, right?
Yes. And then this was a proof that 1 over 3 to the 1 over 3 plus 1 over 3 squared plus 1 over 3 to the 5. Wait a minute. Let me. No. I'm sorry. 1 over 1 plus 1 over 2 to the third plus 1 over n 3 to the third. The reverse third powers of 1 over n squared, where n goes from 1 to infinity. This is an irrational number.
Yeah, that sounds difficult.
No, and the proof is, this is a big achievement of Euler. He gave the example, and he gave a proof which was defective, but his answer was correct. And that from this answer, it follows immediately that it is irrational. And there are other problems like that. And these are, up to this very day, is not solved by any of the elegant methods.
It's only solved by a brute method.
No, Apéry is not. It's an ugly solution.
Right, that's why I said brute.
It's not a group method. It's
no, I said brute.
Brute, yes, by
Yeah.
brute thought.
Yeah.
It takes it's Ramanujan, if you know the name, had intuitions into these kind of problems. This is a kind of results in mathematics which was done by Hardy and Littlewood in the British school and so on. Very complicated, infinite products, infinite sums, all kinds of ratios involving the number pi and all kinds of things, tricks, integration, and so on. Very hard problem, very hard solutions, and they are not beautiful. That's all. This is but the computers which are now being used to solve problems like the four-color problem and Tom Hale's problem, they are even uglier than that, because you give part of the solution to a computer which you take without understanding, have no conceptual access to the problem itself, except of course you know how the computer works.
Right.
So if somebody has intuitions
that's
about...
a huge epistemic problem.
Yes, but look, it depends. If you are the programmer of the computer, then you might get a big satisfaction because you have your own intuitive access
Right.
to, and then you say, oh, that's a beautiful program. That's a beautiful code. Take a code which is written, I don't know, 200 lines of codes, and say that's a beautiful code. I wouldn't be able to say that's a beautiful code, but somebody who is a programmer, who has his own aesthetic criteria and what is a beautiful code and what is not a beautiful code, can say it. Because you see, it has the programmer has a kind of intuitions which gives him epistemic access to areas for which I don't have epistemic access. So he already operates in a different domain than the mathematician who wants a solution to the problem.
Right. Okay, Professor, it's
Okay.
time for me to take the dog out.
Okay.
So before you take those off, though, thanks again so much. These have been,
Okay, sure.
This is the fourth one we've done, and they've all been so
Okay.
fun to do. So thank you so much.
Yeah, it was fun for me. Okay.
I have recorded this about 10 times because I'm just so bad at asking for help. But if you could like, subscribe, comment on whatever medium you're consuming this nascent fledgling podcast on, that would be so helpful, because the best thing for helping me grow this podcast at this point is making it at least appear that I have an audience. So thank you for listening, and thank you for supporting me.